actually go ahead and just go through the do now together. Number 1 is actually part of one of the free response questions from 2018. So it was one small part of a long free response question, but it had to do with Lewis structures and hybridization. So hybridization will let us kind of review the concept, and then I'll go through hybridization a little bit more later. So for this, it gives us an equation, but then it says the skeletal structure of the HNO2 molecule is shown in the box below. And then part 1, complete the Lewis electron dot diagram, that's just Lewis structure, of HNO2, including any lone pairs of electrons. So just in case you see the term non-bonding electrons, that's the same thing as lone pairs. Non-bonding and lone pairs are the same thing. So we're going to go through just like we normally would. Start by counting our valence electrons. So hydrogen has 1, each oxygen has 6, nitrogen has 5. 12, 13, 18. So we have to place 18 electrons in this Lewis structure. When I look at this, I have the potential to multiple bond. The multiple bond between O and N, or N and O. So that means I have to use the 6N plus 2 rule. Remember that N is the number of atoms, not hydrogen. We don't count hydrogen. So it's 3. 6 times 3 is 18, plus 2 is 20. Valence electrons in 6N plus 2 is not the same. If it's a difference of 2 like this, that means that we need 1 double bond. Now, they only gave us 1 structure, so we're only going to have 1 answer. Here's something you need to remember. Write it in green right up here. Oxygen typically forms 2 bonds. So one of the little tips and tricks with Lewis structures, so Lewis structures was chapter 8, is that oxygen typically forms 2 bonds, which means it has 2 bonds and 2 lone pairs. That's going to help us as we're doing this Lewis structure. So I know that hydrogen cannot multiple bond, so that has to be a single bond. Using the idea that oxygen typically only forms 2 bonds, what does this have to be? Single bond. Because if oxygen can only ever form, not only, but typically, only form 2 bonds, 1, 2, which means it needs 2 lone pairs to satisfy the octet rule, which means my 1 double bond will go here. And the reason that we say oxygen typically forms 2 bonds is due to formal charge. If we were to actually calculate the formal charge, this is going to be the best structure for us to have. So 2, 4, 6, 8, oxygen has satisfied the octet rule. This oxygen, 2, 4, 6, 8, it satisfied the octet rule. Nitrogen, 2, 4, 6, still needs 2 more. I should have placed 18 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. This is what the HNO2 Lewis structure looks like. Then part 2 says, based on your completed diagram, identify the hybridization of the nitrogen atom in HNO2. So there's a lot dealing with hybridization. There's orbital overlap, looks at how it forms between the S and the P and the D orbitals. You do not need to know anything about orbital overlap, how they're formed. You just need to be able to identify hybridization. So there's a trick you can use your fingers with, or you can just memorize them, whatever works for you. So when we think about orbital diagrams, the S sublevel has 1 orbital, one of them. The P sublevel has 3 orbitals, 1, 2, 3, and then the D sublevel has 5. So we're going to kind of use that to start. When we look at hybridization, count the area of electrons around the atom that it's asking about. So hybridization of the nitrogen atom, there's 1, 2, 3 areas of electrons. Hybridization is based on the electron domain geometry. So there's 1, 2, 3 areas of electrons. So 1, 2, 3. We said there's 1s, and there can be up to 3p. 1, 2, 3 is s, p, and p. That's sp2. So the hybridization of the nitrogen atom is sp2. So there's a chart in your notes that goes through the hybridization. It's always based on the area of electrons. If you think about it, technically there's a 1 here. We just don't see the 1 because anything to the first power is that number itself. So technically this is a 1. 1 plus 2 is 3. So sp2 is when you have 3 areas of electrons. So you have sp, sp2, sp3, and then you're out of p and you have to go into the d. So then you have sp3d, sp3d2. That's as far as you can go. So it goes from 2 areas of electrons up to 6. We'll look at hybridization a little bit more later. So number 2, what's the difference between an electron domain geometry and a molecular geometry? So remember that the electron domain geometry are the fundamental shapes. So as we're looking at electron domain geometries, electron domain geometry only looks at number of areas of electrons. So the electron domain geometry only looks at the areas of electrons. It's one of the fundamental shapes. So electron domain geometry is only ever linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. That's it. And molecular geometry takes into account lone pairs. So molecular geometry takes into account lone pairs, and we're looking at how the shape of just the atoms change. So electron domain geometry, we're only looking at the number of areas of electrons around. This is a fundamental shape. Molecular geometry then takes into account the lone pairs and looks at how the shape of just the atoms change. So the molecular geometry is some sort of derivation of the fundamental shape. Then number 3, if you complete the 6n plus 2 rule for a molecule and recognize that you can have either 1 triple or 2 double bonds. So we looked at this for carbon dioxide, for CO2. How do you determine which Lewis structure is the most dominant? So there's something that we can calculate. We calculated it last week. What did we look at calculating with the circles? Formal charge. So if you can have a triple or 2 double, that's not resonance. I'm going to review resonance in a little bit. If you can have 1 triple or 2 double bonds, you have 2 different, completely different Lewis structures. To figure out which one is the most dominant, we use formal charge. Any questions on the do now? Trying to review some stuff from like all 4 chapters.
When we did the identifying hybridization, you look at the electron domain geometry. Do you get the S? Okay.
Like to get S, P,
Okay.
sp2, yeah. So just the areas of electrons. So it doesn't matter whether it's a single, double, lone pair. We're just saying here's 1 area of electrons, 1 area of electrons, 1 area of electrons. And we're going to look at that more in a second too. Yeah.
You said you look at the lone pairs for that, like you can. So like how is that different than the molecular geometry?
So then if we were to figure out the electron domain geometry, there's 1, 2, 3 areas of electrons. So 3 areas of electrons, that fundamental shape is trigonal planar. But then the molecular geometry says, okay, well now the lone pair is actually going to repel the electrons in the bond. So instead of looking like this, just based on the electrons, this is now a lone pair. So it's going to actually push these down a little bit more, so now it's bent.
Okay.
Yeah.
Okay.
Oh, okay.
Yep. And we're going to look at, because we didn't get to that practice last week, so we'll go through a lot of the practice today.
Like the oxygens like not do anything same like the top and bottom. Like in terms of like affecting the shape.
Well, so when we look at how anything affects the shape, we are always looking at one of the central atoms. So oxygen and nitrogen can both be considered central atoms. And so when we're looking at the shape, so here how it says around the nitrogen atom, we could also look at the shape around the oxygen atom. And then we have two bonds, two lone pairs, so that's going to be bent as well. Yeah. So when you're looking at identifying hybridization or identifying a shape, whether electron domain or molecular geometry, they have to tell you what atom you're going to be looking at. Before we jump into hybridization, there were some questions on, like within the Ed Puzzle video that said, I don't necessarily have any questions on hybridization, but I do have some on sigma bonds or on resonance structures. So I just wanted to go back through these again. Sigma versus pi bonds. The things with sigma versus pi bonds, you don't have to worry about how they overlap. One is end-to-end, one is side-by-side. You don't have to worry about that. You need to be able to identify how many sigma bonds, how many pi bonds, and that's based on the Lewis structure. So the first bond that forms, no matter what the Lewis structure is, the first bond that forms is always sigma. Every bond after that between two atoms is a pi bond. So if we're looking at ozone here, this single bond is sigma. We look between the other two O atoms. The first one that forms is sigma, which means this one's pi. You have a triple bond. The first one is sigma, the other two are pi. So you have to have the Lewis structure to determine sigma versus pi bonds. That's all you have to do with sigma and pi. The first one that forms between two atoms is sigma. The rest of them that form are pi bonds. So you always have at least one sigma and then potentially one or two pi bonds, depending on if it's a double or a triple bond. Then there were some questions on resonance structures, and not necessarily resonance structures itself, but the terms localized versus delocalized electrons. So when we're looking at something like ozone, we say these are equivalent structures. They're resonance structures. So the actual structure is somewhere between these two. Within resonance structures, you'll notice the atoms stay in the same place. The atoms themselves don't change. What changes is the position of the electrons. So these like this one double bond could move, and then we can have a double bond between the other two oxygens. So when we're talking about localized versus delocalized, the electrons in a single bond, the electrons that are held in place are called localized electrons. They are local between two atoms. So this single bond, these are localized electrons. This single bond, those are localized electrons. They don't move. Delocalized electrons can appear in different places. They can move. So the electrons in this double bond, we would say are delocalized because they appear between these two oxygens in the first structure, and they appear between these two oxygens in the next structure. So if electrons appear in different places, they are delocalized. Just means that they can move.
Would that lone pair be delocalized now?
Yes. So then we would have this lone pair would be delocalized because it moves to the other side. Yep. So when you're thinking, if something ever says delocalized electrons, it's probably talking about resonance structures, because the electrons can move to different places. So within resonance structures, we have both types of electrons. And you'll look at some resonance structures, and by some, I believe there's one resonance structure we're going to be looking at today in the practice as well. So that's looking at localized versus delocalized electrons. So now we're going to look at the hybridization example that's on page 8 of your notes. So it's at the very bottom of page 8, and there's just one question, but it looks at hybridization, and then it asks about the Lewis structure itself. This is a sample AP question. As you'll see, we have a student claiming something again, and we have to agree or disagree. We're starting to ask these on almost every free response question that we see. So before we actually look at the example, something to point out up here. Every central atom has a certain hybridization. And really every atom in a molecule has a hybridization. But we focus just on the central atom. And it will ask us, just like in these questions, about a specific central atom. You don't have to worry about how the orbital overlap works. You just have to be able to identify hybridization. So here it gives us the Lewis structure, and it says that this compound has 2 nitrogen atoms. They labeled one X and one Y. Part A says determine the hybridization of the nitrogen labeled Y. So we're determining the hybridization of this nitrogen down in the bottom. To determine hybridization, count the areas of electrons. So count areas of electrons. So it's based on the electron domain geometry. So if I'm looking at nitrogen Y, just count the areas of electrons. Here's 1 area of electrons. Here's 2 areas of electrons. Here's 3 areas of electrons. So there are 3 areas of electrons. So you could do 1, 2, 3. Remember, you have 1s, 3p, and up to 5d orbitals. So 1, 2, 3. S, p, and p is sp2. Or again, if you want to just memorize the chart that's in your notes. So we will have 2, 3, 4, 5, 6 areas of electrons. 2 areas of electrons. 1, 2 areas. sp. We would say it's sp hybridized. So you can only have 1 s orbital. You can have up to 3p orbitals. So 3 areas of electrons. sp2 hybridized. That means that 1s and 2p orbitals have to come together. You don't have to know how they come together. You just have to know there's 1s and 2p orbitals that come together. 4 areas of electrons. 1, 2, 3, 4. We can have 1s, 3 p's. sp3. So if it's a tetrahedral electron domain geometry, it's sp3 hybridized. Well, now we've run out of p orbitals, right? 1, 2, 3, 4, 5 areas of electrons. We have 1s, 3p. Now we're into the d. 5 areas of electrons is sp3d. 6, we're adding another d orbital, sp3d2. This is all we have to know for hybridization. Areas of electrons, what the hybridization is. That's all you have to do. So then B says, the student claims that all of the atoms in the molecule exist in a single plane. Do you agree with the student's claim? Justify your answer. So I'm going to use this model just to show you what it means by do the molecules exist in a single plane. Something like trigonal planar. All of these molecules exist in the same plane. There's really no molecules coming at you or coming to the back. So if you think about like an XY axis, they exist in the same plane. Something like tetrahedral. So notice the difference between these. With tetrahedral, you have a molecule coming out, or an atom coming out at you. So even though we have one going up and two going to the side, there's one coming at you. These molecules are not in the same plane. Trigonoplanar is tetrahedral. They're not laying in the same plane. So if we look at really nitrogen X or Y, with nitrogen X, we have 3 atoms bonded to the central and 1 lone pair. It's going to look like this. 3 atoms bonded to the central and 1 lone pair. All of these atoms in this molecule do not lie in the same plane. There's a 3-dimensional structure to it. So for part B, here's what we're going to say. I'm going to put it up here so that everybody can see it. We're going to say that we disagree. So we can say nitrogen X. So we had already looked at nitrogen X. Is sp3 hybridized. Nitrogen X had a tetrahedral electron domain geometry. So it has a tetrahedral electron domain geometry. Not all atoms are in the same plane. So if it were in the same plane, like nitrogen Y, even though there is a lone pair, this is what nitrogen Y looks like. 1 lone pair, 2 atoms bonded. This is really like a 2-dimensional structure. There are no atoms coming out towards you or coming back away. Nitrogen Y, all the atoms in this part lay in the same plane. But once we get to tetrahedral, or trigonal bipyramidal, they're not going to lie in the same plane. Okay, so that was just kind of a sample question. Lying in the same plane means we're looking at 2-dimensional versus 3-dimensional structures. All right, so now you guys are going to have some time to work. So for the rest of class, you have the rest of this period and next period. You can get with a partner or with a small group. And there are 2 different things that you can work on. So first, we're going to start with the hybridization practice. So that's page 9 in the notes. I have the answer key linked up here. I also have it put on the board up here. So for that, there are 6 Lewis structures. So you'll draw the Lewis structure, you'll name the molecular geometry and the electron domain geometry, and then give the hybridization. Then you can go back to pages 6 and 7. Pages 6 and 7 were the table that had you draw the Lewis structure, look at the electron domain and molecular geometry, as well as if the molecule is polar or not. So it gives you some practice with molecular polarity. Same thing, I have the answers linked here, or they're up on the board. And then just if you kind of want to start looking ahead, you're going to notice there's no videos for you to watch. The only thing is to start reviewing. So you can work on the Unit 1 review. Again, I have the answer key linked up here. The unit review is like a practice test. So one of the best ways to review is to work through the review. I do not pick it up. I don't give you points for it. It's strictly for you to practice. I would also recommend looking at the weekly reviews. So I'll return the one that was due this morning. But weekly review 3, 4, and 5, we're on chapters 6, 7, 8, and 9. So you can go back and you can look at the feedback for those. The weekly reviews are going to be really good ways to study as well. So once you get that feedback in your email, if you don't have like an AP Chem folder, maybe just make a folder in your email so you can put it in there. You can go back and review those. And then finally, the last page of each notes packet, you had 4 notes packets for this unit, 6, 7, 8, and 9. The very last page of each notes packet is a what you need to know page, where I take essentially what the AP curriculum says you need to know, and I type it all out. That's another really good way just to review the different concepts, because our tests are like AP tests. So I'll leave this slide up on the board. You can move around, work with other people. You can come up